some lectures on classical mechanics, maybe quantum mechanics and electrodynamics. So let me start with what is the aim of statistical mechanics. Oops. So there's a world around us, and you can ask, and there are many length scales involved in the world around us. For example, there are length scales even smaller than that. Let us take atom to be the smallest length scale we are interested in, and then there's the largest length scale, which is the size of our universe. And we sort of sit here every day, that's our everyday life. The distances are meter, centimeter, kilometer, that scale. What is this scale? Can we estimate the length scale of an atom? Can we estimate the length scale of what's the size of a universe, meaning our universe? So, so why don't we estimate the two limits? So first let us ask, what's the typical size of an atom? And I'll tell you, carbon has a density 1.2 gram per centimeter cube. With this information, can you take 1 minute and estimate what will be the size of an atom? Do a small calculation. Given that density of, let's take carbon as an example, and I give you the density, how many grams per centimeter cube. And if I ask you, given this, can you estimate the size of a, estimate means not the exact answer, but rough order of magnitude of a carbon atom. Just do some small calculation, whatever comes in your mind, just try for 1 minute. Any suggestions of how we are proceeding? Yeah, but how do you determine the volume? Agreed. So let me outline what he said. So all of you are told that 1 mole of some material has Avogadro number of particles, and that 1 mole weighs its molecular weight, which is 12 grams for carbon. Okay, so, but now we are also told that 1.2 gram occupy 1 cc, that's the density of carbon. So now 12 grams occupy 10 cc, 10 centimeter cube, which if I convert to meter cube is, you multiply by 10 to the minus 6. So now Avogadro number of particles is in this volume, 10 to the minus 5. So 1 atom occupies a certain volume. Okay, so that is the argument. So this is 10 to the power 28 minus 28 by 10, roughly this answer. So that's L cube. So I can imagine each atom is enclosed in a cube of size small l. So L cube is this volume, which is roughly 10 to the minus 30. So if I take cube root of that, the interparticle spacing is about 1 angstrom. So, so that is the distance between two carbon atoms. So you can take that to be the size of a carbon atom also. Okay. So when you are interested in the atomic scale, the distance scale is angstrom, 10 to the minus 10 meter. What about the size of the universe? So size of the universe also, we can make a rough estimate. So we are told that the age of the universe is 10 billion years, which is about 10 to the power 10 years. And the size of the universe, if you want to make an estimate, you can say that is the distance light has traveled in this much time. So the size of the universe is that, and even though Indumati told you speed of light is 1, it is actually 300 into the power 8 meter per second into the number of years, 10 to the power 10, 365 days, and roughly 10 to the power 5 seconds per day. If you put these numbers, you get 10 to the power 26 meters as the size of the universe. So, that's the answer to our, we are interested in physics of physical world from 10 to the power minus 10 meters to 10 to the power 26 meters. So, the range of scales is a ratio of 10 to the power 36 meters. 10 to the power 36 is a huge number. So, depending on our interest, we will focus maybe here, maybe we will focus here, here, and so on. Okay? And at different length scales, you have different physics depending on the material or system you're looking at. Now, just like time scale, just like length scales, there's a lot of time scales also we're interested in. So, for example, if I look at the vibrational frequency of atoms, then the time scale involved is picosecond, 10 to the power minus 15 seconds. On the other hand, if I look at the time scale associated with the universe, it's order of millions of years. That's like 10 to the power 5, 10 to the power 10 years. So, if I take this ratio, again it's a huge number. So, depending on the time scale and length scale, you can have a wide range of scales in which we can focus our interest on. So, just as an exercise, I wanted to estimate, suppose I take a gas like nitrogen and I put it in room temperature 300 Kelvin, standard pressure, standard temperature, what we call STP, and I give you Boltzmann constant is this value. Can you estimate the time of collision between two particles? So, if I take nitrogen gas or oxygen gas, the gas around us, can we estimate what's the typical time of collision between two atoms? If I give you, if I give you Boltzmann constant. So, can you just take 1 minute and try to see whether you can work this out? This is using your knowledge of ideal gas. You know, there are many things you learn about ideal gas in the beginning. Treat it as an ideal gas and try to find out. And we also know that the distance between the molecules are roughly 1 angstrom. So, what you need to do is find the speed. Is it possible to compute the time? So, what is the rough speed of a molecule, order of magnitude in this room, for example? Is it 1 meter per second, 100,000 or 1 kilometer per second? What is it? 1 meter per second. Any other estimates? Sorry? Smaller than that. So, the calculation is, let's do a calculation. So, you know, when you do ideal gas, you are told that each mode of meaning if you ask what's the energy per atom, per degree of freedom you have half kT. So, if you ask what's the energy of kinetic energy of a molecule is 3 by 2 kT, and that's half mv square. So, all we have to do is find V from here. So, I have put 12 here for carbon, it could have been 16 or 14 for nitrogen. So, it is 12 grams divided by number of molecules in a mole. Hydrogen, okay, hydrogen, nitrogen, all of them are sort of similar. I said nitrogen. So nitrogen and hydrogen difference is, let's say instead of 12 you get 1 or 14. Okay. So if I divide by the Avogadro number, I get the mass per atom into 10 to minus 3 to convert it to meter into V square is 3 by 2 into K. I gave you K before, and temperature is 300 Kelvin. Okay. And then you can just simplify. You get V is roughly 700 meters per second. Okay. So it is moving, the speed is quite high, but does it mean, okay, at the side, even though the speed is of this high, does it mean that this molecule, this atom is reaching there and back in 1 second? The speed may be 700 meters per second, but it undergoes many collisions in between. So the actual motion is not ballistic, it's something else, but this is the speed. So if I ask what's the time between two collisions, is length by speed. Length is roughly 1 angstrom by roughly 10 to minus 12 seconds. Okay. So that was just to give a that this number, this is of course the vibrational scale. That was just to show that this number is not some, out of, you can believe that number. Okay. Now, so the main point is that you have different phenomena. So what I argued now is that we are interested in a wide range of length and time scales, and you see different phenomena at different length and time scales, and I'll give a few examples of them. So one well-known example is a collection of particles interacting through short-range interaction. So which is your gas molecules. Okay. So at the length scale at 1 angstrom, they are like hard spheres. They go about, when they see each other, they collide elastically and move out. Okay. But if I look at centimeter scale, or meter scale, like this gas, like this room, then I don't see molecules. I see liquid, solid, or gas. In this case, gas. And I no longer talk about the position that there's a particle or not. I talk about pressure, temperature, and density. Okay. So if I were interested in the micro scale, I'll talk about the position and moment of each particle. But when I come to a larger length scale, I forget about all that. I have a description in terms of pressure, temperature, and density. Okay. And to work with a gas at this scale, I don't have to know anything about what the constituents are. I can make some laws connecting pressure, temperature, and density based on empirical rules and continue from there, and things should have been fine. Okay. So, the point is that this is the example to show that depending on which scale you're interested in, the description is different, the number of degrees of freedom are different, and how are they connected, we do not know. Okay. Another example is, suppose I take a solid and pull it with the force this side and force this side. There are some atoms inside. They may be interacting, they may be moving around, jiggling, and so on. I do not see them. It need not even be atoms. I could have a model where I make a connection of springs inside and I pull them from top and bottom. But when you talk about such a system, we talk about stress, strain, and some elastic moduli inside here, C. It could be Young's modulus, rigidity meaning shear modulus, I don't know, rigidity modulus, something, and so on. But when engineers work, they are not bothered about what atoms are inside. They are only bothered about what is this C. And once you are given this C, you can make buildings, you can make, I don't know, you can construct everything. Your whole buildings are standing on this particular relation. Okay. So here there are maybe maximum you have to give is 6 or 7 material properties. At this level, you have to give the momentum and, I don't know, position of a large number of particles. Okay. And as before, one could start from here, make empirical laws and work forwards like this, or one could derive them from here, we do not know. So these are not the only, these are standard examples, but we could have more esoteric examples. You could have rocks becoming planets, becoming galaxies as you change scale, or molecules at the nanometer scale becoming protein, cells, tissue, organ. So, for example, if I want to know the contraction and expansion of a heart, I can plot its signal, I can make some rules for that. I do not have to know that in the very inside there are molecules inside interacting. People, they join to form society, and lot of society becomes a country, agents become a market, and neurons may interact through exchanging electrical signals within each other, but when there are many of them, you have a nervous system and a brain and so on. Okay. Now, when you, as the length scales are crossed from micro to macro, a lot of new emergent phenomena come. So, for example, we talked about pressure, which is not there at the single atom, single particle range, entropy, consciousness. Two neurons, there is no consciousness. Millions of neurons, suddenly you have a consciousness. So, you cannot talk about consciousness at the micro scale, but you can talk about consciousness at the macro scale. Rigidity, culture. Single person, no culture. Society, there is a culture. Okay. So, therefore, it is not enough to say that if I understand the interaction between two particles at the fundamental interaction, that is enough. It is not enough to know that, oh, two quarks are interacting with some interaction. That interaction is not relevant at a scale which is centimeter. You have new phenomena, new. So, sometimes a lot of things are taught where you reduce things. Oh, if I understand the interaction between two things, I can work out the other one. I can work out many interactions, which is not true. So, a lot of new phenomena come when you put in a large degrees of freedom interacting microscopically. Okay. Now, what is the role of statistical mechanics? So, given this background about what are we interested in, what is the role of StatMech? Does it help in, so if I give you set of particles, does it help you give you the interactions? The answer is no. It does not help you to give the interactions. What it does is, it tells you that if I want to understand the macro scale from the micro scale, StatMech tells us how to do that. Okay. So, if I want to understand what is the equation of state for a gas, can I start from the microscopic interactions and derive that? So, how to do this derivation of starting with interaction between two particles, put many of them together and derive the macroscopic properties, that is the role of StatMech. Okay. Is this clear? Okay. We will do a few examples later on, meaning once, so you have to know how to do this. Once we know how to do this, then we will do some examples and find out some maybe interesting phenomena. So, in addition, you can have multiple macroscopic phases. For example, you can have gas, liquid and solid. But when I change temperature slightly, for example, I am not changing the interaction between the particles per se, but when I change the temperature slightly, it might go from liquid to solid. There is an abrupt change in phase in the macroscopic level, while at the microscopic level you are not doing anything much. So, how does one understand changes in phase from one to another, phase transitions? Can StatMech help you understand phase transitions? Okay. So, these are two broad, so understanding the macro phases and understanding the transitions, there may be many more, but this is the broad aim of StatMech. It could be a physical system, it could be a social system like markets, it could be a biological system like yourself. The system is not important, it gives you a way of going from one scale to another scale. Okay. Now, is this part okay? If something is not clear, please tell. Now, there are broadly two classes of problems. One is equilibrium StatMech and the other is non-equilibrium statistical mechanics. I will mainly do equilibrium StatMech because equilibrium StatMech problems are easier to do. So let me define precisely, or roughly, what is equilibrium. So over the course of observation time, none of the averages change with time. So if I take a glass of hot water and keep it here, after some time I keep measuring temperature. It's initially 100 Kelvin, 100 degrees centigrade. After some time it is 35. Then it doesn't change with time. Then I say, oh, the temperature doesn't change with time. It may have reached equilibrium. But of course, if I do over many days, it may not be true, because after some time water will start evaporating. So when you say things are in equilibrium, you have to also tell within some measurement time scale, things don't change with time. Okay, so that is one criteria for equilibrium. But is that enough? So let me look another example. I have a rod like this. One side is kept at temperature T1 and one side is kept at temperature T2. Then I wait for a long time. These temperatures are kept fixed. Then I ask, if I measure the temperature at different points, what will it be? So after a long time, you can imagine that one side is at T1, one side is at T2, and there is a linear extrapolation between the two. This graph does not change with time, just like before. But lack of it, even though it does not change with time, there is some heat being supplied from here to here and being taken out here. So there is a heat current in the system. So this we will not call as equilibrium. So we will call problems of equilibrium ones in which things don't change with time and there are no currents in the problem. Okay, that's a technical thing, but that's important. So this will be our definition of equilibrium. Okay. Now, equilibrium problems are easier to study, but generically, since things are out of equilibrium, for example, if I take a human body, you have to keep eating to give energy to the system. The energy is dissipated through heat and work, but if you stop eating, you will not be able to sustain your life. Okay, the whole thing is based on an energy current in the system, and therefore which is true with most of the things you see around you. So most things are out of equilibrium, but they are more difficult to study also, and so it's better to first understand equilibrium systems and then understand things out of equilibrium. Okay. Now we will do a small calculation to understand what happens when you increase the degrees of freedom from 2 to 3 to 4 to infinity. What changes when you add degrees of freedom? So you will have to do the calculation. I'll ask questions and you have to do the calculation yourself, and hopefully we will understand something from this small calculation. So I have a box of volume V of n particles, dilute gas. Okay, so a dilute gas, so they interact infrequently. I will model it as an ideal gas. Ideal gas, all of you are familiar with. So I have a ideal gas in a volume V with capital N particles. Now I am going to do measurement. So I take a small volume delta V here, and I keep observing how many particles small n are there. So I make one measurement. There are small n particles. Then I know my density is n by delta V. Number density is n by delta V. So I keep doing this measurement, and then you ask what's the density, and I can always tell you what is my current density. Is it clear? This is now when delta V is very small, let us say size of 1 angstrom, that is the size of order of the atom interparticle spacing, and I plot, so I am keeping on measuring, what should I expect n as a function of time to look like? So let me pose the question again. I have a small volume which is order 1 angstrom cube, and then I keep asking. So when I make a measurement, I may see 100 particles, then I plot 100. The next time I plot something else. So what would I expect if my delta V is very small, order of 1 angstrom cube? Highly fluctuating, and most of the time what will you see? Fluctuating about 0 or 1, because it is unlikely that you will see many particles, as he said correctly. So often you will see 0 particles. Sometimes you will see 1 particle, because the volume on average has 1 particle. Sometimes 2, sometimes 3. It looks like this. Do you agree with this plot? It seems okay. Now, then I would say density is either 0, 1 by delta V, 2 by delta V at different times. But normally, if I were to ask you what's the density of gas in this room, you will give some answer. Of course, this is in mass density, 1.27 kilogram per meter cube. You are not going to give some value which says, it could be 1.27, it could be 1.53, no, currently is 1.02. You don't say that. No, you always say it is 1.27, a more or less a precise value. So this doesn't seem right. This plot doesn't seem so right. So I change my delta V a bit more. Suppose delta V was larger, then you may have 6 particles, sometimes 4, 5, 6. The plot looks something like this. But even here, if I ask you what's the density at any point, you will get some answer 4 by delta V, 0 by delta V, a large fluctuation here, and you are not. This is not what you expect. But if I were to make delta V larger and larger, for example, I take half the box size, then you would expect that when you measure density, it looks like this red curve. It fluctuates about some average line, a little bit above, sometimes a little bit below. How much above and below we do not know, but this is the sort of plot we would expect as you make delta V larger and larger. If somebody expects something else, they can tell. This graph I drew just from the fact that we say the density is 1.25, which means if I make a measurement, it might be 1.26, but not 1.53. Okay, so the plot might look like this. And this blue line we'll call the average density, and then there's some fluctuation about that. Is it okay? So now, what we have done is we have changed delta V, made larger and larger. So can we quantify? Can we quantify how it goes from very discrete like image to something which is almost flat? So let us try to quantify this graph. So suppose I pick a particle at random and I ask, what's the probability I'll find this in delta V? What's the answer? So the system is the ideal gas is evolving in time. I pick particle number 1 and I ask, what's the probability I find it in delta V? No, I have given a delta V. What is the probability? Sorry? Delta V by total volume. Because the particle has no preferred position in the box. It could be anywhere in the box equally likely. So the probability of being in small delta V is delta V by the total volume. Right? If that is the case, what's the probability of the given particle not being in delta V? Is 1 minus delta V by V. Now, the position of one, if I take particle number 2 and I ask its probability, does it depend on the position of particle 1? No, because all the particles in ideal gas are independent. So if I ask the probability of if particle 1, okay, what's the probability of particle 1 and particle 2 being inside delta V? Is a square, and the square because they are independent. If they were not independent, there will be some modification for that, but we are taking them to be idealized gas, so therefore it is delta V square independent. Given this, what's the probability of 0 particles in delta V? Now I want to ask, now I make a measurement, what's the probability there are no particles in delta V? Yeah, it is the probability that no particle is there, which is 1 minus delta V by V to the power n. Because probability of first particle being not there is 1 minus delta V by V, second particle 1 minus delta V by V the whole square, and so on. Okay. Yes. This is a well-defined probability because it is less than 1. It is this probability is either there or not there. The two should add up to 1. They should both be positive. This is positive, and it adds up to 1. So it is well defined. This is not a continuous distribution because it's either there are only two possibilities, two discrete possibilities.
I mean, wouldn't we actually take the difference of V minus delta V by the total volume for the second one, because we know it can't occupy the same position?
No, so this is an ideal gas, so we have removed that. There is no
two particles can occupy the same position.
Yes.
In space and time.
Yes, otherwise the calculation is not easy.
Right.
Otherwise, if there's an exclusion, this is not true.
But even in ideal gas case, like they have, we consider them to be non-interacting, but they can't occupy the same position at the.
No, in the ideal gas, so ideal gas by definition, there is no interaction. They have no size. They can occupy wherever. Just the generalization of a hard sphere will create some more corrections to the ideal gas equation. So we are taking the extreme limit of ideal gas where there is no even exclusion. Okay. Okay, so that is right. So the probability of 0 particles is 1 minus delta V by V to the power n. That is, the first particle should not be there. That's 1 minus delta V by V. Second also should not be there. Third also should not be there. The probabilities multiply and you get this answer. What about probability of exactly one particle? Sorry? Into NC1. Okay, so that is the right answer. So let me just tell different people to different answers. So probability of so now let me write a bit more. Let me do. Okay. So if I ask probability of 0 particles in delta V, it is 1 minus delta V by V to the power n. All of us have agreed to that. Now our delta V is going to be very small compared to the total volume. It's a small test volume. So I want to take the limit when delta V by V is small. So I write this as e to the power n log 1 minus delta V by V. Then I expand log 1 minus x is minus x, which is e to the power minus n delta V by V. But n by V is fixed. That is my number density of the ideal gas, which is e to the power minus rho delta V. Is this calculation clear? This is expanding log 1 minus x as minus x for x small. Now, probability of one particle, exactly one particle in delta V is, I pick a particle, it is in delta V by this probability, the others are not in delta V with the probability of 1 minus delta V by V to the power n minus 1. But then I have a factor NC1 because I can choose which particle I want to be in delta V. I can choose that in n ways, one particle out of n. And now I again do the same trick. So NC1 is n by v is rho. This delta v becomes here, that is rho delta v. Here I exponentiate e to the power minus rho delta v comes again. There is a factor -1, but that -1 is multiplying delta v by v, and that goes to 0 in the limit delta v by v going to 0. Okay, so that is, so the answer gets modified. Now I can put two particles. So two particles are exactly same argument. Two of them are inside, product of two, product of n minus 2 of them, NC2 to choose two of them. NC2 is roughly n square by 2. I can combine with this one to get this answer, and this one combines again back to e to the minus rho delta v. So we are left with half rho delta v square. Now once you do this much calculation, you can write down what's the probability of k particles, and it turns out to be this answer, rho delta v to the power k by k factorial e to the power minus rho delta v. If some derivation is not clear, I can just do it right on the board. So this is the answer in the limit delta v by v is small and k is finite, 1, 2, 3. Is it okay? Now we have, this is valid for k equal to 0, 1, 2, 3 up to infinity. So we have to do some basic checks. So what are those checks? First is that if it is a probability, it should sum up to 1. So first of all, let me write it as lambda to the power k by k factorial e to the power minus lambda, where lambda is rho delta. Is everybody following? Is somebody, if any question is there, please ask. Okay. So now, what's the question again? In a small volume delta V, what's the probability we find k particles? And the answer was this. To make it easier to write, I write lambda to replace rho delta V. Now, first thing I can check is this sum up to 1? So if I sum from k equal to 0 to infinity, lambda to the power k by k factorial is e to the power lambda, and there is e to minus lambda sitting outside, so they cancel out to give you 1. So it's normalized, and this distribution you have seen before. Even if you have not seen before, it's called the Poisson distribution. Okay. So now let us derive a few things about Poisson distribution. So given a distribution, you can either work with the full distribution, or you can compute the moments, first moment, second moment, third moment, and so on. So let me do a small calculation for first moment and second moment. So I have a so what is the definition of first moment? Expectation value of k, which is summation over k times p of k. Now p of k is this Poisson distribution. So I want to do this sum, summation over k, lambda to the power k by k factorial. You may have all done this before, but just for doing one last time. So I know that summation over lambda to the power k by k factorial is e to the power lambda. So whenever I want to find moments, you have to differentiate with respect to lambda. So when I differentiate with respect to lambda, I get k lambda to the power k minus 1. I multiply by lambda, I get back this one, and I differentiate right hand side is e to the power lambda lambda. Okay. Then I take this e to the power lambda this side, and that's the answer I want. So expectation value of k is lambda square. Okay. So there's only one parameter in the Poisson distribution, and that parameter happens to be the mean value of the random variable. So k is called the random variable because that's the one which is not, whose value keeps changing with realization. Is this okay? Okay. So now once you have done this, if I want to compute expectation value of k square, all I have to do is differentiate this one more time. If I differentiate this one more time with lambda, I get k square lambda to the power k minus 1. I multiply by lambda again, and you get expectation value of k square. So that is this differentiation. So you people should try it yourself. and if you do k square, you get lambda square plus lambda. So that is just by differentiating this particular expression with respect to lambda. Okay, and you get expectation value of k square is lambda square plus lambda, but this we know is expectation value of k the whole square, and this is lambda. So if I take k square minus k average square, it is lambda. What is so important about k square minus k average square? It says this is the fluctuation in k. Okay, the most dominant term in k square is k average square. If I subtract that out, I get what is remaining is the fluctuation. Okay, so Poisson distribution, the mean goes as lambda, the variance also goes as lambda. That is the point. Okay? Any? Okay. Now, so with that much in mind, let us try to plot P of k, which is this quantity, as a function of k for various lambdas. So small lambda, large lambda, and so on. So suppose lambda is small. For example, I take lambda to be 1. If I take lambda to be 1, I get P of k is 1 by k factorial. 1 by k factorial decreases with k. Okay, it is k equal to 0 is 1, k equal to 1 is 1. I take lambda equal to 0.5. Then if I plot P of k versus k, it decreases with k. It is maximum at k equal to 0. Average value is lambda, which is somewhere here. Okay. So the most likely event is here, k equal to 0, but the average value is not the most likely value. There is a difference between the two. If I make k slightly larger, let us say lambda equal to 2, then it looks like this. The maximum has moved away from 1, but there is a non-zero probability at 0, finite probability at 0, but the maximum moves away from 0. Okay. Now, if I make lambda even larger, then the plot looks like this. The mean value is lambda, it peaks about lambda, and it looks roughly like this. Now, the typical value and the average value will turn out to be the same, but the distribution looks very different from here. Okay, this is just sketching, this is just taking the Poisson distribution and looking at small, intermediate, and large lambda. So in one of them, the maximum occurs at k equal to 0, the other one just moves away, and the third one it moves far away from 0 and peaks at some point lambda. Now, what case should we analyze? Of course, I have written here analyze this case a bit better, but remember our lambda is rho delta v. So should we analyze small lambda, large lambda, or intermediate lambda? Now, to do that, we need to put some number. Is lambda dimensionless or dimension full? Because its number of particles per unit volume into volume is dimensionless. Now, is lambda going to be large or small? So let us do a calculation. Let us say our probe is really small. Our probe is 1 millimeter cube. Okay, I am sitting in this room, but our probe is really a very small probe, 1 millimeter cube. What is rho delta v? What is lambda for this value 1 millimeter cube? Can you estimate that? So what is rho delta v? Is the number of particles in the volume 1 millimeter cube. So that's your lambda, and I'm asking, if my probe is a very small probe, is lambda going to be large or small? Yeah, but large as in what number will it be, roughly? Is it like 10, 20, 100? Sorry? 10 to the power? 40. 14. So a really large 10 to the power 14 is the aim. So let us do a rough calculation for that. So again we go back to your ideal gas, what you learn. 22.4 liters at room temperature and pressure occupy is occupied by 1 Avogadro number, 6 into 10 to the power 23. So, if I take 1 millimeter cube, which is our interest, 1 millimeter cube is that number divided by 22.4 liters converted to meter cube into 1 millimeter cube, which is 10 to the power minus 9. Then 23 minus 9 is 14, plus 3 17. This is by 4, roughly 10 to the power 16. So, so lambda is 10 to the power 16 even for a very small probe that you put in. So, it makes sense to analyze lambda large, not lambda small, but to analyze lambda large. Remember, for lambda large my claim was that it looks like this. So, we are going to analyze this case a bit better because that is the interest that we have.
When we are getting the Poisson distribution, that time we have to assume that delta V by V was small, right? So can we still make that approximation when we are considering large?
No, we are not considering large. Delta V is small compared to capital V. So, there is a large volume, we are taking a small volume inside, and then you can make this other volume go to as large as you want. But this volume, now you are comparing with the interatomic spacing L and saying it is much larger than that. So, there are two limits. So, delta V by V is going to 0, but delta V by L cube is going to infinity. Okay. So, now let us analyze that one a bit better. So, now we are going to analyze for lambda much larger than 1. So, this is our Poisson distribution. Now, our distribution looks like this. So, now I am going to ask, I know we have already done the calculation that expectation value of k is lambda. So, now I ask what is the probability that k takes a value different from lambda. Let me call that value as x, this distance as x. So, I write k is lambda plus x. So, I am asking what is the probability that my actual value k is different from a mean value lambda by a quantity x. So, this is not, so now what I want to do is I want to find probability of this x. So, I ask, I take this Poisson distribution lambda to the power k by k factorial, I substitute k equal to lambda plus x. So, p of x becomes lambda to the power lambda plus x, e to the power minus lambda and lambda plus x factorial. But remember, your lambda is very large, and now we are going to assume that x is much smaller than lambda, which you have to check ultimately. Okay. Now, so how to analyze this particular quantity? You have a factorial outside, downstairs, but this factorial is a large factorial of a large number, and there is a nice formula called Stirling's approximation, which says that n factorial is root of 2 pi n to the power n plus half e to the power minus n into corrections of order 1 by n. Okay, so we will just say we will replace this factorial by this first quantity here. Is it okay? So, I again go back here, lambda to the power lambda plus x, I write it as it is, e to the power minus lambda I write as it is. This one I write as root of 2 pi, n is now lambda plus x to the power half, e to the power minus lambda minus x I put it upstairs in the numerator. Okay. So, now you can see this lambda and this lambda cancels out, and we have to e to the power x root of 2 pi, and then I take out this lambda outside. Lambda is much larger than x, so I get lambda into 1 plus x by lambda, but okay, maybe I should do in the, okay, it's okay, you can figure out. There is a lambda to the power lambda plus x plus half, which cancels out this one, leaving a root lambda outside. What is remaining is 1 plus x by lambda. Oh, I skipped one more step. Okay, maybe I should do this on the board. Can you see if I write here? If I write a bit big, lambda to the power lambda plus x by e to the minus lambda. I am using Stirling's approximation for this one. So, this is roughly equal to root of 2 pi lambda plus x So, this is from Stirling's approximation. So, this becomes equal to this e to the minus lambda cancels with this e to the minus lambda x, and then there is a root of 2 pi. I pull out lambda, and I am left with 1 plus x pi lambda. So, these cancel out. Okay. And here, and now we are going to use that x pi lambda tends to 0, or x pi lambda is, so this becomes e to the power x and e to the power lambda plus x plus half with a minus sign log of 1 plus x. So, I have just exponentiated this one. Now, log of 1 plus y, where y is small. So, the expansion is log of 1 plus y is equal to y minus y squared by 2. This is Taylor expansion of this kind. We just apply this here. So, this becomes equal to e to the power x 2 pi lambda e to the power into y is x pi lambda minus x square by 2 lambda square. If I want to keep the next term, there is x cube by lambda cube, but you will realize, okay, let us keep plus order x cube. Let us keep it like this, which is now first term I multiply lambda with this, I get minus x, then minus lambda into plus this one, so plus x square by 2 lambda, then nothing more, plus x square minus x square by lambda plus order x cube by lambda square. This is small compared to this one. Okay. There is another term half x by lambda. What is that? That also has gone to 0. Okay, plus half x by lambda. Is this okay? Now, this e to the power x cancels with e to the power x. So, I am left with e to the power minus x square by 2 lambda by root of 2 lambda. Then there are many other terms here, x by lambda, there is x cube by lambda square, but we are going to work in the limit when x square by lambda is finite. So, we had decided that x by lambda is much less than 1, but I'm going to say that x square by lambda is finite. Suppose I do this, then x cube by lambda square is equal to 0, x by lambda also goes to 0. Okay. Why? X by lambda is, we already said it's much less than 1, so this goes away. X cube by lambda cube is x to the power 4 by, yeah, it is, this is even smaller than, yeah, this over. Is it clear? If I keep x square by lambda finite, all the other terms go to 0. So that is the answer. Okay, so when I make lambda large, I again come back to, where was I? Okay, that was a bit messy, but so we started with Poisson distribution, and we just decided that we are interested in the case where lambda is very large, and then we just put lambda large and looked at deviations about lambda, and we got this formula as a probability for the variation of the difference of k from lambda has a distribution which is e to the power minus x square by 2 lambda by root of 2 pi lambda. Okay. Now, so now few checks. This this function is a Gaussian. Okay. It says the deviations from the mean is described by a Gaussian. First thing you can check is that if I integrate from minus infinity to plus infinity, I get 1. Root of pi by 1 by 2 lambda, it integrates to 1. Second is that if I compute expectation value of x, it is 0 because it is it's a plus minus symmetry. Third is if I compute expectation value of x square, if you do this integral, do the same trick, differentiate with respect to a and do the things fast, then you will get that your variance of x square is lambda. Okay, then, which is true because the variance of x square is the same as the variance of k. So what have we done? We derived the exact formula for the number of particles in a small volume delta V. Then we took the limit when lambda is large, because in any probe we put in which is much larger than the microscopic scale, your lambda becomes very large. In that limit, we showed that the Poisson distribution becomes like a Gaussian centered about lambda. That is our claim. Okay. So now given the distribution, you now are measuring, every time you measure how many particles are in delta V. What did you expect? You expect your n to lie between these 2 points, right? Most of the time. Sometimes you may get some answer here, but most of the time when I measure k, I get some answer that lies between lambda plus minus the width of this distribution. So if I were to write it, I would say n, typically the value of n will lie between lambda, the mean value, plus and minus the width, which is root of x square, the standard deviation, which is lambda plus minus root lambda. Yeah.
That it will be a Gaussian, but far from that we still have to.
Far from that we have to still compute, but
when we do that integral from minus infinity to infinity, then we are taking x to like cases where x is very large and we can't approximate the probability distribution.
not true. So what we have done is we have found the answer by taking the limit x going to x large, lambda large, keeping x square by lambda fixed. Then you get some answer. Now after getting that answer, now you can make that limit go to infinity. So the limit, the order of limits, once we take the limit, after that the integral, so ideally when I integrate p of x, you are saying that my limit should ideally be from, because we took x square by lambda is finite, we should go from minus some c times root lambda to plus c times root lambda, something like this. No? That should be the correct way of doing it, because we are keeping x out of root lambda. But lambda is already large. So this is equal to minus infinity to plus infinity p of x plus minus some correction terms, which is 0 to minus infinity to minus c root lambda minus c root lambda 2. This you will be able to show is actually goes to 0 when lambda goes to infinity, because that this you should be able to show.
Pi was x square by lambda finite?
Because when we expanded, we got this as a leading term. If we didn't keep x square by 2 lambda finite, then we wouldn't have got a sensible answer here. We would have got either infinity or 0. So that is the only reason. Okay. So now, so with all this calculation, let us come back and ask how many particles do we normally see, typically see when we make a measurement. So we decided that most of the time, most of the probability is contained between lambda plus minus standard deviation. Maybe a bit more, maybe a bit less. Maybe you can put a factor 10 here. It does not matter. So I'll say lambda plus minus the width, which is we found exactly to be root lambda. So this is my answer. Then I measure my density. My density is n divided by the volume delta V, which is lambda by delta V plus minus root of lambda by delta V. But this quantity, because lambda was rho delta V, lambda by delta V is rho. So when we measure, we typically get rho plus minus lambda is rho by delta V. Agreed? I have just substituted for lambda equal rho delta V. So if I multiply by delta V on top and bottom, I get rho plus minus rho by root of rho delta V. This is my lambda. So this calculation, once we do the calculation, this is what we are going to get every time we measure density. But we just decided that if rho delta V in any measurement we do is extremely large number, but it comes in the denominator, which means that this number is almost 0. So this number is almost 0, which is why we get a curve like this with the fluctuations. So if I put delta V, rho delta V to be order of 10 to the power 16, then if the density is some number, I get a correction 10 to the minus 8. So if I take rho outside, rho into 1 plus minus 1 by 10 to the power 8. So in the 8th decimal place, you get a correction. So in case this itself is a exaggeration, the blue line is what you will see, and that is why when I look at number of particles in a thing, I do not worry about density being different from its mean value. Is it clear? So changing delta V is like changing the number of particles you are averaging over, and when the number of particles become macroscopic, many things become extremely well defined. So that is why when you talk about thermodynamics also, you don't talk about temperature, you talk about temperature being one value. You don't say it is 305 Kelvin, oh no, 303 Kelvin, the same reason. We will do one more example of this later and try to formalize why large numbers, sorry? Oh, phone, okay. Okay, so that is my, so let me summarize. I had some comments to make. Okay, so before that, let me just pose it in a slightly different manner. So similarly, if I want to measure pressure, how would I measure pressure? I'll put a probe somewhere. Then I'll ask, so when a particle comes and hits the probe and goes back, it changes momentum. Then you say how much momentum is rate of change of momentum per unit time, per unit volume area is the pressure. So if my probe size is very small, let's say 1, or I make my measurement in femtosecond time. Every femtosecond I make a measurement. Then most of the time no particle hits it. So its pressure is either 0 or some large amount. Then I increase my pressure from measurement time 10 to minus 15, 10 to power 8, let us say 10 to minus 8. Then you will see some maybe 100 particles hit in time, in the time of measurement. Then if I make it order of seconds, then 10 to the power 10 collisions occur in that small measurement time. You are summing over all these particular momentum changes. Once you do that, then your pressure is a well-defined value. But it became a well-defined value because in your measurement time, there are order of 10 to the power 12 collisions occurring. Okay. So we will try to formalize this next time in the form of central limit theorem. Why is it that when your number of particles or degrees of freedom become larger and larger, your measurements become more and more precise, and you can talk in terms of macroscopic variables. Okay. So let me now ask while we are here and there is time. So this is the typical values of density of CC. But is it possible to get, even with this calculation, is it possible to get 0 particles in the volume delta V? It is possible. There is a probability. The probability is e to the power minus okay. So what is probability of 0? Is e to the power minus lambda, which is e to the power minus 10 to the power 13 or 16. An extremely small number. But if I were to do this is some huge number, but there is still that small probability that suddenly there will be 0 particles in that. Okay, so your density might look like this. This is density as a function of time. So it will go like this, and suddenly it can go down like this and come like that. It is possible. It is a very rare event, but it can happen. But if it happens here, next time when I measure density, I am back to the normal. It's a probability distribution. I may have a small probability here, but if I measure something here, most likely my graph will be here, not here again. So is it clear that it is still possible that you have, it's like saying, if I let the system evolve in time, in that corner there are no molecules. It never happens, but it's possible to happen. Now, suppose I had this plot like this, and I create the system in the beginning. Now I'm thinking of a different system. I create the system in the beginning where there are no particles in delta V. Suppose I'm able to create such a system. Will the system know that I created the system like that, or it occurred due to a natural fluctuation? So I am sitting here, the system spontaneously evolved so that in the volume delta V there are no particles. Now you consider another system, another scenario. In this scenario, I by hand have no particles in delta V, and then the system evolves in time. Will the system know how this was created? Was it a spontaneous fluctuation or was it a man-made fluctuation? It doesn't know. If I run the system forward in time, it will come back to this position. Is it? So sometimes, so that explains why. So in fact, if somebody shows you a movie of like that, you will know that this is future, this is past, because of this reason. And therefore there is some irreversibility split into the system, because when large numbers come, there is some irreversibility that comes into the system. This point I'll clarify, explain, we'll discuss one more time. You also do some thinking, and then we will try to understand why, when I increase number of particles, irreversibility automatically comes into play. Okay. Now, so let me summarize. So the first point was that knowing fundamental interactions are not enough. So it is not enough to say that these two particles at the nanometer scale interact by Lennard-Jones interaction. It is not enough. It is not enough to say that the quarks have some interaction between them, because when the degrees of freedom increase and the scales change, new emergent phenomena come which we are not able to guess by knowing the fundamental interactions. That's point number one. I think that we are convinced. Then the role of StatMech is to ask how to bridge these scales. It is applicable to both equilibrium and non-equilibrium. And we did a small calculation to show that when the measurement scale goes beyond the microscopic scale, how macroscopic quantities become well defined. So that calculation, I'll stop here. Okay, so that was any questions?
Number of, like say the density can drop to 0 discontinuously.
Not discontinuously,
It
continuously.
would have to drop continuously, right? So in that process, wouldn't there be a point where it wouldn't be able to drop any further because there's like say the pressure because of there being like a vacuum essentially or something like that?
Yeah, we are not talking about the temporal reasons for why it became 0. In our calculation, what we did was that there is some system, we are having a probabilistic description of that system, not a description in terms of how the system is evolving in time. And then we did a calculation which said that if I make a measurement, I have these probabilities of getting the answer. There is a probability of getting 0 also. How that system goes to that 0 state, that I do not know, but there is a probability of getting 0. You are asking how can it ever become 0, because there will be some flow issues and so on. Maybe, but we are not even talking about that. No, each particle in an ideal gas is flowing independent of each other. It is just running around here and there. By some coincidence, none of them come to delta V.
Right. So both processes, I mean the same process can be described either through probability or as a dynamical process, right? Like in time.
We can, but if I go through the dynamical process, I have to describe all the degrees of freedom.
Right.
Oh, so maybe that point also I should make. So if I were to do the microscopic description, then I can have a deterministic description of all the momenta and position. But that is not, then we also argued that at the macroscopic scale, we are not interested in all of them. We are interested in 4 degrees of freedom, density, pressure, temperature. So it makes no sense to follow them. But we lose a lot of information, and in that process, the description becomes probabilistic. So we lost a lot of information, and our description also changed with time. We have only a probabilistic description from now on. Was it too fast? No.
Sir, like as you said, knowing the fundamental interactions are not enough, and many new emergence phenomena arise when the scale shifts. But knowing the fundamental interactions and the laws of physics, can we modulate the emergent phenomena?
Yeah, that is the role of StatMech.
Okay, sir. So can it be done reverse? Like knowing the emergent phenomena, knowing the large scale phenomena and the laws of physics, can we find the fundamental interactions?
Yeah. So for example, suppose I want to get a system that is moving a solid. I want to have stress equal to E times strain. Now I can put in atoms. I can imagine a system where atoms are moving around and they have some Lennard-Jones interaction. I can also imagine a system which is just some springs connected to each other. They will give, both of them will give the same answer above. Both of them give the same macroscopic behavior. So in this process of coarse graining, we lose a lot of information. So it's like a many to one interaction. But on the other hand, so if I look at macroscopic behavior, for example, I take van der Waals gas. So van der Waals gas has P into V minus B is A by V, something like that, no? V plus V minus P into V minus V, P plus A by V square. Now there are two constants there, A and B. Now you can ask this by itself, if I start with this equation, I can work from there. I say I fix A and B from experiment. Or I can ask, if I give you my microscopic interactions, can I compute A and B? So, but there are multiple microscopic interactions that can give you the same A and B. So it's not possible to go backwards like that, but you can rule out, you can say that this kind of interaction gives you this kind of macroscopic behavior, and this kind of interaction gives you this kind of macro, but by using StatMech. But you cannot precisely say if this is true, then the microscopic interaction must be this. Is not possible. But so let me give the logical part. So if I start with a microscopic interaction and I get a macroscopic behavior B. So A, microscopic behavior A implies macroscopic behavior B. Now what if I say, can I say something about A? Tell me. If A implies B, does not A imply not B? Sorry? No. If A implies B, then not B implies not A. Correct? So if I know that if I put in this microscopic interaction, I get this microscopic behavior. If I don't see that microscopic behavior, I know that's not that microscopic behavior cannot be right. That's I can say. No, that's not the case, but this you can see. Yes.
The graph which we showed for the smaller lambda values, in that it's continuous graph.
Yeah.
So
Yeah, so that is not correct. It should be actually discrete. But then you must
or is it a cumulative probability?
no. So where was my job? You are right. So P of K is discrete. So I was a bit careless in the. I'll write. I cannot run. So P of K will always look like this. No? Whatever, even if the Gaussian one, so it will look like this. Now, what is this? What is continuous? So we are now defining a variable. We are looking at probability of K, what is our x? X is equal to lambda minus k. K equal to lambda plus x. Here also x is discrete, right? But now in the limit where, so we are defining a variable y. So ideally what we should do is we should define x square by lambda. So x square by lambda is a variable y equal to x square by lambda. Now this variable, as you increase lambda, becomes more and more finely spaced. X is still discrete, but x square by lambda, what is delta y? Delta y is 1 by lambda. This spacing becomes more and more finely spaced, So if I were to plot P of y, which is our correct variable, that variable becomes more and more finely spaced and becomes continuous. So this is the, so when you plot a scale variable and you take the limit lambda going to infinity, that variable becomes continuous. I was a bit careless in plotting that, and when I make lambda larger and larger, it becomes like this, but you should have plotted a scale variable there.
And also in that moment generating function, I guess we have some errors, sir. Like e power lambda we taken in, e power lambda is equal to x lambda power n by n factorial. And you said we are differentiating with respect to lambda in both the sides.
Yeah.
And in right hand side we got lambda e power lambda.
So this we wrote as e to the power lambda.
Yeah, if we differentiate it with respect to lambda on right side, it should be just e power lambda, right?
Yeah, but e power lambda, but I want k lambda to the power k by k factorial.
Yeah, I got it.
So I put, I just skipped as, I have to do lambda d by d lambda. So let me tell what we so in the, so next thing I'll do is I'll try to make the statement about central limit theorem. So that's an important result to know. Why, when you increase the number of particles very large, how universality comes in. The other thing is I will discuss a bit of irreversibility, also some philosophical part. Then StatMech, many people might have done courses and so on. A lot of the coursework is trying to motivate why certain calculations are done. We will forget about those motivations. We will try to summarize what are the working rules for computing. I think that is what one should know, and then do some non-standard examples of how to compute them. I think that will make something clear, and then we can proceed from there. Okay, we'll stop.
Rajesh, can I just add a comment on this reverse engineering question?
Reverse engineering.
Yeah, so this question on reverse engineering, so this is going slightly outside StatMech, but a whole lot of model building community exists also. I am a high energy physicist. This model building community exists in high energy physics and also in other physics as well. What we try to do is we observe certain phenomena and try to actually come up with some fundamental interactions, some model of fundamental interactions, try to see whether this model succeeds to post-dig this observation. Now let's say if there is a set of models that post-digs this set of observation, now we take these set of models and try to predict something new, and try to say it to the experiment saying that, okay, you see our model is successfully predicting this thing. So now if you can actually check for this thing, and if the experiments actually find it, then the model goes successful. And you also can actually rule out certain models. So this basically falsifying that theory. So these kind of things exist, reverse engineering. So if you get to speak with many other faculties here, you'll get to hear a lot of different kind of discussions on this. But the question was nice, thanks. Okay, now it's just announcement, a set of announcements. So there will be tea outside. One card, credit card or debit card was actually, means someone got it. Vijay Lakshmi is the name in that. So in case if you have lost it, just contact